This is the default interface you will see when you open the Salome software. First we have to create the CAD section, then after that meshing procedure. So in order to create the CAD section, we have to go to this drop down menu and click on this geometry. So first I will create a box, click on this icon, then I will create a box with the dimension 18x, 15y and just 5 in Z direction. Apply and close. And in order to create the free and fixed region, we have to separate these regions. For that I will first create a cylinder with radius 8 and thickness 5. Apply and close. Then I will translate this cylinder to 3 locations, here, here and here. This will be the force phase and this will be the fixed locations. For that, go to operation, transformation, translation. The x dimension 10, y is 10, apply and close. So that object is placed there. Similarly, select the cylinder, go to translation, 10, this time 40 in y, apply and close. Again clicking on this cylinder, translation, 17x, 25 in y, apply and close. These 3 objects created. Next we have to make a union of these 3 objects of translation. Press this icon, fuse. It will create a boolean union of objects. Apply and close. A fuse one object is created. Next step is we have to remove this section from the remaining section of box 1. For that we are going to use this cut operation. The main object is box 1 and the tool object will be fuse 1. So this will be our free region. In order to create the fixed region, again I will create a cylinder with radius 5, thickness 5, and I will translate the smaller cylinder as similar to the previous one. 10, 10, apply and close. Again repeating 10, 40, apply and close. Sorry, deleting that. Selecting the cylinder 2, translation, 10, 40, apply and close. Yes. Again selecting cylinder 2, translation, 17x, 25 in y, apply. So we have created 3 objects. Then create a fuse from these 3 objects. Next what we have to do is we have to make a cut from this fuse 1 object with this fuse 2 objects. So go to cut, main object is fuse 1, tool object will be fuse 2, apply and close. So this will be our fixed region and this will be our free region. So with these 2 objects created, next thing is to create a compound of these 2 objects. So select cut 1 and cut 2, then go to compound, apply and close. So in this stage what we can do is we can go with the meshing procedure, but one problem will exist, that is the self intersection. So if I select this compound 1 object and go to inspection, detect self-intersection, some self-intersection detected, and it will greatly affect the FEM results. If we go for FEA, structural FEA with the calculate solver, then after running the solver, when we view the result, we can see the stress concentration nearly here in this boundary between the free the boundary between the free and fixed region. We will see stress concentration that has to come to this wall, but it will be shown here. So in order to remove that problem, what we can do is select this compound 1, go to repair, glue faces, apply and close, hide this object, select this glue 1, again go to inspection. Now you can see there are no self intersection in the shape. Now we have already prepared the geometry, we are good to go, but one more procedure is there. We have to make some group, solid group, face group. For that, select this glue 1, go to new entity, group, create group. First we have to create solid region, so click on this solid object, name the first group as free region in capital letter, free region, and select the region that we need for optimization. So free region is created. Again select glue 1, go to new entity, group, create group, select the solid object, then again create a fixed region, this time fixed region, and select the appropriate solid objects. Apply and close. Yes. Next thing is select the face group and name it as first fixed face, where we'll apply the constraint. Select this one and this one, apply and close. Next, one more group where we'll apply the force. Select the face, name it as force face. Main object is the glue 1, and select this and apply and close. It is glue 1, it is okay. So the CAD section is almost completed. Now we can move to the meshing stage. For that we can move to this mesh module, where we'll create the mesh. So now we are in the mesh module. We'll go to this create mesh, then select the gmesh, tetrahedral, go to gmesh parameters. I'll make the maximum size as 2, and here you have to make your concentration. We have to make a second order quadratic element, otherwise the Python script will not convert the data into INP format. If it is a linear, it will not convert to INP format. So in order to convert to quadratic, click on this second order option. OK, apply and close. Again we have to create the mesh group inside here. With the main object is mesh 1, first we have to create the free region, apply and close. It will comes under the volume region. Again fixed region, apply and close. Both are solid, that's why it's come under the volume. Again go to mesh 1, create groups from geometry. This time select only the force face, apply and close. It comes under group of faces. In the next time select this mesh 1, go to mesh, create groups from geometry, select this under nodes, select this fixed face. So it will create only a group of node, and this one we will use for calculating the C load, means concentrated load on each node. So the next thing, everything is okay, we have to compute the mesh. So it is started computing. Now it has completed the mesh generation without any error. So you can see the generated mesh. Now in order to run the Python script, we have to ensure that it is quadratic. How we will check? Just right click on the mesh information, element info. You can see on each face, each edge there will be 3 points. On each face it is 6 points, which means the solid mesh will be 10 noded tetrahedral element. So we are good to go. So close this. Then next thing is we have to run the Python script. For that I have already prepared a Python script. So click on this ccx writer1.py. What that script include is, it is a file format that extract the Salome data and convert it into, into INP format of calclix input file. So here the name of the file and its path I have given here, that Salome 2 ccx demo to INP format. So when I run this Python file, it should show the, at the end it should generate the INP file. So I am clicking on this ccx writer1.py and click on open. So it's writing completed, and if I go to the folder, then you can see it is already generated demo to INP format dot INP file, which is the name that I have given here, demo to INP format. So the next thing is to run this INP file using the calclix solver. Usually the command is ccx space name of the .inp file, excluding the .inp option. You don't have to include the .inp that ending, you just have to mention the name of the file. But here I am using the ccx solver compiled for precise. Precise is a coupling solver where we can use different fluid structural solver together for running multiphysics optimization or multiphysics simulation. So for when you are using calclix solver, you just type ccx, that's it. For my case, I'm already installed for precise, so I'm using some extension. For your case it will be just ccx space the name of the file, here it is demo. Exclude this INP ending and click enter. Now it will run the simulation. The solver is calclix. Now it is finished. This is the output file we can view through FreeCAD software. So how we can do that? Just open the FreeCAD software, locate the direction to the folder where the .frd file locates. Click on open. So it will generate the result object. If we double click on this, we can see the simulation result as similar to what we have seen in the FreeCAD initially. So we have run a FE simulation with data taken from Salome software. The problem of this self-intersection. This is the FreeCAD result with an iteration 39 for a cantilever, where it is okay. One side is tension and one side is compression equally in the structure, equally the stress is distributed. But if there is self-intersection in the CAD part of Salome, then the problem arises in the topology optimization result or FE analysis result. Here you can see the low stress region, but this region is higher even though the force acting is the same. So that you have to be careful. There should be no self-intersection before proceeding to mesh operation. Also, the C load implementation applied here. Initially I have applied equal force on every node in the force phase, but there is a different implementation in FreeCAD how to apply C load. C load is a syntax for calculus for applying concentrated loads on each node. So for that there is a implementation. You can check here how to distribute the load on each node using this implementation. And this is the Python file that I have created. I will upload this file to Patreon under $10 tier. If you are interested, you can download from that. So this is the way for pre-processing for topology optimization using FreeCAD and Salome software. Next tutorial I will include the processing stage in topology optimization, how the data is flowing such that the low stress region is removed while maintaining the high stress region, so that at the end we will see a bionic shape like this. How these shapes are generating in topology optimization. This is the blue one is the low stress region and the red one is the high stress region. How this structure is generating I will discuss in the next topology optimization series.